guys, it's Mrs. Allison. Today we are going to look at adding and subtracting radicals, but as I mentioned before, oftentimes the ACT will put a simplifying radicals type problem on their test. And so I found one, and it is the warm-up that we're going to start with. So go ahead and take a second and see if you can simplify that square root of a cubed b to the fourth c to the fifth, and see if you can determine which answer it is. All right, hopefully you had a chance to try that problem. And there's several ways that we can approach this. If you want to look at this as three separate problems, we could certainly do that, where we look at the square root of a cubed, the square root of b to the fourth, and the square root of c to the fifth. Okay? And in doing this, if you look at them separately, maybe even you simplify these further to get the perfect squares. So the square root of a squared times the square root of a. The square root of b squared, square root of b squared. And then the square root of c squared, square root of c squared, square root of c. Maybe we go through and do that. And in doing that, hopefully you notice that the index and the power are the same on quite a few of these, actually. Okay. Now, what we talked about is when we have an even index or an even power, what we have is the absolute value, because we want to make sure our answer stays positive. So you might think, okay, well that should be, that should be the absolute value of a, root a. Maybe this is the absolute value of b and the absolute value of b, absolute value of c, absolute value of c, root c. And then you look around and say, well, I don't see that answer. Even if I were to simplify it, I don't see all these absolute values in there. Hopefully, though, you looked at this and said, okay, if I have the absolute value of a, that has to be true. And then what happens when I have two of the same numbers being multiplied together? Well, it would be the absolute value of b squared. Okay, well, if we square a number, is there ever a chance that squared number is going to be negative? Meaning, is there anything I can substitute in for b that when I square it is going to be negative so that I need the absolute value sign? There isn't. So really we can just say the absolute value of a times b squared. Similar argument for the c squared, the absolute value of c squared, we can just write as c squared. And then I have what's left is that's a c, ac. And so my answer would have to be b. How'd you do? Okay, there's just an example of what the question might look like on the ACT. Okay, so let's look a little bit more at simplifying radicals, and I want to review again the idea of rationalizing the denominator. For whatever reason, this tends to be the hardest part about the division, and so let's look at that. Sometimes our denominator is a little bit more wonky than we looked at yesterday. And so we still need to think about that conjugate pair. And so for this problem, I do not know what just happened, but for this problem, I am going to multiply by root 5 plus root 2, the conjugate of root 5 minus root 2. So if I multiply both numerator and denominator by root 5 plus root 2, it looks like this. Distribute on the top and we get 3 square root of 10 plus 3 square root of 4. Of course, that can be simplified. Over, now let's multiply these. We would get the square root of 25 plus the square root of 10 minus the square root of 10 minus the square root of 4. Okay, that's what it looks like initially. Now let's simplify it. We get 3 root 10 plus 3 times 2 because the square root of 4 is 2. And then we have root 25, which is 5, minus root 4. Minus root 4 would be minus 2. So finally we get 3 root 10 plus 6 over 3. Ooh, that can be simplified even more. And so we get root 10 plus 2 over 1. And of course we could leave off the over 1 part. So this rationalizing, the whole point of rationalizing, remember, is that our goal is to get rid of any square roots in the denominator. So we multiply by that magic 1. And the magic 1, when we have these crazy fractions like this, is going to be the conjugate pair. So multiplying by root 5 plus root 2, because this one was root 5 minus root 2. And then simplifying. All right, hit pause and try this second one and see what you come up with. Okay, after looking at this next problem, what am I going to multiply by? What is going to be my conjugate? It's going to be 3 plus root 6. And when I FOIL this together, when I multiply, distribute, however you want to look at this, I'm going to get 12x plus 4x root 6 over 3 times 3 is 9 plus 3 root 6 minus 3 root 6 minus root 36. Now remember, the whole point of rationalizing the denominator is to get rid of any radicals in the denominator. So let's see if I've accomplished that. We would get 12x plus 4x root 6 over 9 minus 6. So we get 12x plus 4x over root 6 over 3. And that's as far as this can be simplified. So this is my answer. How'd you do? Okay, let's move on to the last property we're going to talk about as far as these basic radical properties. Let's look at the sum and difference of radicals. Okay, when we look at the sum and difference of radicals, there's a few key things that we have to pay attention to. In order to be able to add radicals together, two things must be true. They must have the same index, and they must have the same radicand. If either one of those is off, then we cannot add the radicals together. So if the radicands and the indices don't match, we can't add them. When we do add these together, a times the nth root of x plus b times the nth root of x looks like this. I keep doing that. Looks like this. A plus b, in parentheses there, times the nth root of x. Okay? Picture it like you're adding variables. If I had 2x plus 3x, like terms, I'm going to add 2 plus 3 and multiply it by the x. So I'm going to get 2 plus 3, which is 5, and get 5x. It's exactly what we're doing here. Just my variable may look a little bit different. It may be in that radical form. So let's look at a pretty simple example. If I want to add 2 root 5x plus 3 root 5x, the first thing I want to check is to make sure that my index is the same. And if my index is the same, then I want to check to make sure that my radicand is also the same. And since both of those hold, they are both the same, I am now going to take and add the two numbers in front and write the root 5x after it. Now we probably wouldn't leave it 2 plus 3 because we know what that is. So adding these together, we get 5 and then times root 5x. So try this next one. Hit pause, try it. A little bit different because it's got a variable outside, but see what you come up with. Okay, can these be added together? Well, their index is the same and their radicands are the same. So I am saying we can add these together. So now I'm going to add my two terms, my 5 plus my x outside. And then I'm going to write the cube root of 17xy. And I've done it. I've simplified this as much as I can. I cannot combine the 5 plus the x anymore. And maybe, actually, let's look at this just again. Maybe I'm going to put that cube in there a little bit tighter so it doesn't look like it's a power. Mine kind of looks like a power there. Those say the same thing. These are equivalent, but the cube root is notated just a little bit better. Okay, but guess what? This works. We can add or subtract radicals even if they don't look the same to begin with. Here's how. Let's first make sure that all of my indices match. Start there. We can clearly tell that the radicands don't match. 12, 75, and 3 are not the same. But they all three have the same index. So the next step now is to see if maybe, just maybe, we can simplify these radicals just a little bit. Meaning if I take the square root of 12, means I'm doing the square root of 4 times 3, which gives me 2 root 3. And then I'm going to do the same thing with root 75. I'm going to simplify it. This is like saying the square root of 25 times 3, and the square root of 25 is 5, so I have 5 root 3. And then minus root 3, I cannot simplify it any. Hey, look at that. If you look at these now, they all have the same index, just 2, or the square root, and they now all have the same radicand. So now I can just go through and add or subtract whatever it says, just like up above. I now can combine the 2 plus the 5 and the minus 1 to be multiplied by root 3. Okay, why minus 1 though? Well, it says minus 1 square root of 3. Even if we don't write it, and the number's still there, it implies that it's a 1. So really what I have is 7 minus 1, so I have 6 root 3. That is the simplified version of root 12 plus root 75 minus root 3. Okay, the next one is a little bit more tricky in that the index is 3, but hit pause and try it and come back and see how you do. Hopefully you had a chance to finish this. Let's see what we can do. Remember this time, so the first thing I'm going to look for is my index, my indice, and I notice these are all cube roots, so we're good. I can add these together. Well, then we got to put the brakes on, and I can't actually add them together because at the moment, they are all three very different index. So, just like before, I'm going to work to simplify these. And just like before, I used the wrong pen. So if I simplify these, we get the cube root of, well, if I'm looking for perfect cubes, remember I want to think about perfect cubes that I know go in there. Remember 1 cubed is 1, 2 cubed is 8, 3 cubed 27, and you could keep going. I would at least know your perfect cubes up to 5, which is 125 times 2. So I know I could rewrite cube root of 250 as the cube root of 125 times 2. They say the same thing. And I just so happen to know the cube root of 125 is 5. So what I'm left with is the cube root of 2. So 5 times the cube root of 2. Now let's repeat this process. A perfect cube that goes into 54. Well, one of my perfect cubes is 27, And I know 27 times 2 is 54, so the cube root of 27 is 3. I have 3 cube root of 2, and we're good. We've got one more. So if we simplify this one, I could use 8, and the cube root of 8 is 2, so this is 2 cube root of 2. Look at what we see. Now what we see is that my index, let's use the problem below, are all the same. Additionally, now all my radicands are the same. So we've simplified it, so now I can combine the like terms and say 5 plus 3 plus 2. 5 plus 3 plus 2, cube root of 2. Or 5 plus 3 is 8 plus 2 is 10, cube root of 2. How'd you do? All right, hit pause and try this last one. All right, notice that, again, each of my indices are the same. Squared, or square root, square root, square root. So we're good there. Well, my radicands are not the same, so what I'm going to do now is I am going to simplify. Well, the square root of 28 is the same as the square root of 4 times the square root of 7. 2 root 7. Minus, well, the square root of 175 is 25 times 7. And we know the square root of 25 is 5. So we get 5 root 7. And then root 63, we get the square root of, we're doing square roots, square root of 9 times 7. So we get 3 root 7. So when I combine the like terms, I get 2 minus 5 is negative 3. Negative 3 plus 3 is 0. So I get 0 root 7, or just 0. It's kind of a bummer. It's a lot of work to get just an answer of 0, but that is correct. All right. Hopefully that clarifies the idea of adding and subtracting radicals just a little bit. And now you are set to try your homework. Have a good day.